You're the lead network engineer at a growing tech company. The CEO just dropped a bomb. Our network keeps crashing when we add new offices. We need it to handle 10x growth without breaking. Your gut says you've seen this before. Another snapshot of the same pain points from previous chapters. IPv4, IPv6 fighting, Ethernet frames wandering, spanning tree protocol leaving bridges in the dust. Now it's time to zoom out. Instead of tweaking individual protocols, you need blueprints, architectural patterns that turn chaos into engineered reliability. This chapter isn't about memorizing layers. It's about understanding the why behind every cable, switch, and router. You'll learn how to design networks that don't just work today, but scale tomorrow. And yes, these patterns show up on the CCNA exam. Specifically, Topic 1.2, Describe Characteristics of Network Topology Architectures. Let's dive into the 4 real-world architectures you'll face: star and mesh topologies, 2- and 3-tier campus LANs, spine-leaf data centers, and SOHO setups. Imagine you're setting up a small office. 5 computers, 1 printer, 1 internet connection. How do you wire them? The simplest answer: star topology. Every device plugs into a central switch. The switch becomes the hub. Everything else is a spoke. It's clean, it's predictable, and when one cable dies, only that device goes dark. But what if you're connecting 6 routers across a country, each one needing direct access to every other? A full star would require a central hub the size of a small building. That's where mesh enters the picture. In a full mesh, every device connects directly to every other device. With 6 routers, that's n-in-1 pers 2 equals 15 links. Double the routers, quadruple the connections. Reliability skyrockets, because if one path fails, multiple alternatives exist. And then there's partial mesh, the compromise. Certain devices get full mesh connectivity, while others don't. You'll spot this pattern between access and distribution switches in campus LANs. Access switches connect to both distribution switches, partial mesh, but not to each other. Most networks are hybrids, mixtures of these patterns. Your job? Recognize the recurring shapes and choose the right one for the job. Now, scale up. A campus LAN serves users across multiple buildings: a university campus, an office park, a corporate HQ. Cisco's answer: hierarchical design. 3 modular layers, each with a specific job. Access layer, where end hosts connect. PCs, phones, cameras, door locks. This is where security lives. Port security, DHCP snooping, DAI. QoS marking happens here too. Mark early, let the packet carry its priority downstream. Distribution layer, the border between layer 2 and layer 3. Access switches trunk up to distribution. Distribution routes to the WAN and internet. This layer aggregates connections. And crucially, it provides redundancy. 2 distribution switches, 2 uplinks, first-hop redundancy protocols like HSRP, core layer, only in large designs. When you have 3 or more distribution blocks, a full mesh between them becomes a maintenance nightmare. Enter the core. High-speed switches that forward packets at line rate. No security processing, no QoS marking, just raw speed. The core trusts existing markings and moves packets fast. A 2-tier, collapsed core, LAN, combines core and distribution into one layer. It's ideal for small to mid-sized sites. A 3-tier LAN adds the core layer for massive scalability. The layers are modular. Add an access block, plug it in. Add a distribution block, connect it to the core. This modularity is what lets networks grow without exploding. Let's zoom into two-tier design. Only two layers: access and distribution. The distribution layer wears two hats: distribution and core. Hence, collapsed core. Access switches connect to both distribution switches, partial mesh. Distribution switches route between VLANs, run HSRP for redundant gateways, and run OSPF to share routes with the core or WAN. The Layer 2-Layer 3 border sits at the distribution layer. Access to distribution links are Layer 2 trunks. Distribution to core, or distribution to WAN, links are Layer 3 routed ports. Why does this matter for the exam? Because you must know what lives at each layer. Access does security and PoE. Distribution does aggregation, routing, and redundancy. Core does speed. 3 or more distribution blocks? The full mesh between them is too complex. Add a core layer. In a 3-tier LAN, each distribution switch connects to every core switch, full mesh. Each access switch connects to both distribution switches, partial mesh. The result? A clean, scalable hierarchy. Core switches are the express lanes. They forward packets based on existing markings. No STP blocking. Everything is Layer 3. Everything forwardable. OSPF runs between core and distribution. The core is fast, reliable, and boring. Boring is good. When scaling, you add distribution blocks and connect them to the core. You add access blocks and connect them to distribution. The core never sees access switches directly. This separation of concerns is what keeps the design clean. Campus LANs solve north-south traffic, client to server. But data centers? They're built for east-west traffic, server-to-server communication. Virtual machines talking to databases, application servers talking to caches. The traditional 3-tier campus design creates bottlenecks for this pattern. Enter spine leaf, also called close architecture. 2 layers, spine and leaf. Every leaf connects to every spine. No leaf-to-leaf connections. No spine-to-spine connections. The path from any server to any other is always server, leaf, spine, leaf, server. Exactly 2 hops across the fabric, or 1 hop if they share a leaf. Predictable latency. Predictable performance. Scale by adding leaf switches. Connect each new leaf to every spine. The fabric expands without changing the hop count. East-west traffic flows freely. This is the standard for modern data centers. And yes, it's a major CCNA exam topic. Not every network needs a 3-tier design. Sometimes a single wireless router is enough. A SOHO network, small office, home office, has 1 to 10 users. A wireless router combines router, switch, firewall, and wireless access point into one box. Maybe a modem too, depending on your ISP. It's cheap, simple, and usually works. But there's no redundancy. One device fails, everything goes down. One internet connection fails, the business stops. For a small business, that's acceptable. For an enterprise, not even close. SOHO networks prioritize cost over reliability, and that's okay. Right tool for the right job. Let's recap the patterns that shape real networks. Star topology. All devices connect to a central switch. Simple, common, and the foundation of most LANs. Full mesh. Every device connects to every other. Maximum reliability, but the link count grows quadratically. Partial mesh. Some devices get full connectivity, others don't. You'll see this in access distribution relationships. Hybrid. Most networks mix these patterns. Campus LANs use hierarchical design. Access layer, end hosts connect here. Security, PoE, QoS marking. Distribution layer, aggregates access switches. Layer 2 - Layer 3 border. Redundancy via HSRP and OSPF. Core layer, high-speed forwarding for large campuses. No processing, just speed. Two-tier, collapsed core, access plus distribution. Three-tier, access plus distribution plus core. Data centers use spine leaf for east-west traffic. Every leaf connects to every spine. Consistent two-hop paths. Scale by adding leaves. SOHO networks, single wireless router, cost over redundancy. The architect's mindset: choose the pattern that fits the scale, traffic pattern, and budget. There's no universal best. There's only right for this job.